Sometimes if you want to explain what elements belong to a set, you can just list them. But sometimes it's more useful to explain how the elements of the set are related to each other. One way to do this is with a partially ordered set, or a poset. Let's start with an example. Let's look at the subsets of integers 1, 2, 3. So I could list these. There's the empty set, 1, 2, 3, and maybe I'll leave off the bracket, the braces and the commas and sets. So this is the set really containing only the element 1. We've got the set containing 1 and 2, the set containing 1 and 3, the set containing 2 and 3, and the whole set containing 1, 2, and 3. So it's a list of all the subsets of 1 through 3. Maybe a nicer way to write this is to show which sets are contained in which other sets. So we have 1, 2, 3, 1, 2, 1, 3, and 2, 3. So these 2 element sets are all part of that 3 element set. And then this 1 element set is part of those two element sets. This 1 element set is part of those 2. And this 1 element set is part of those 2. And finally, the empty set is a subset of everything. So this shows the 8 subsets of 1, 2, 3 in a diagram that just helps us visualize how they're related to each other. Let me do another example. Let's look at the set of all binary words of length 3. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. I guess we can count in binary until we get to 1, 1, 1, which is 7. So 4, 5, 6, 7. So that's one way to list them. We could also compare these 8 words by comparing the digits component-wise and saying that we'll put one word above another word in the chart if component-wise all the letters in the second word are greater than or equal to the components in the first word. So let's define A1, A2, A3 to be below B1, B2, B3 if AI is less than or equal to BI for all I. So to put these in a chart that way, 1, 1, 1 would be at the top, and 0, 0, 0 would be at the bottom. And then 1, 1, 0, 1, 0, 1, and 0, 1, 1 would all be below 1, 1, 1, because if we compare component-wise, we've got equal, equal, this is less, equal, this is less, equal, less, equal, equal. So these all go below that one. And then 1, 0, 0, 0, 1, 0, 0, 0, 1 would go down here. Those all go above 0, 0, 0. This goes below that one and that one because we have equality in the first position, and then less and equal and less. This goes below that one and below that one, and this goes below that one and that one. So it turns out that this is actually the same diagram. So these diagrams are called partial orders, and maybe before I give this definition, I have to define one more thing. So we call the lower element in a diagram if we're comparing two less than a higher element. Alright, I just cheated and paused the video for a second so I could get a lot of stuff out of the way and put these two posets next to each other. So we have elements that are less than each other in this poset. Let's call this one P and this one Q. So 2 is less than 2, 3 in this poset, and 0, 1, 0 is less than 0, 1, 1 in this poset. Now we can see that these posets are the same thing. That is, they have the same shape. We call posets isomorphic, which roughly is Greek for same shape. I don't speak Greek, but it's something like that. If there is a bijection, so a perfect matching of the elements in one poset with the elements of another poset, let's say phi from P to Q, such that x is less than or equal to y in P if and only if phi of x is less than or equal to phi of y in Q. So we can see the bijection here. I've pretty much drawn it to make it clear. And I can explain what the bijection is in words by saying the bijection is subset S gets mapped to the word with ones in positions S. So the set 2 goes to the word 0, 1, 0. The set 2, 3 goes to the word 0, 1, 1. One's in positions 2 and 3, or one in position just 2. A rough idea of what bijection means, other than this, is that we can pick one of these pictures up and put it down on the other one exactly. Now let's draw all of the possible partial orders on a 1 element set, a 2 element set, and a 3 element set. This is an 8 element set that we draw a poset on. So let's start to draw posets on n element sets. So if n equals 1, there's only one element, so we can't do much with it. N equals 2, we could have 2 elements, neither of which is greater than or equal to the other, or one element less than the other. For n equals 3, we could have 3 elements unrelated, We could have two elements that are related and a third one on the side. We could have one element greater than the other two, one element less than the other two, or we could have one element greater than a second, which is greater than a third. For n equals 4, well, maybe I should point out, so far the number of posets on n elements is a Catalan number. At least for n equals 1 through 3. That won't quite work for n equals 4, but let's write out the posets and see how many there are. So we have 4 elements with no relations between them. We could have one element greater than a second and 2 unrelated elements. We could have one element greater than 2 others, or one element less than 2 others. We could have one element less than 3 others, or one element greater than 3 others. We could have relations between the elements that give us this shape. We could have one element less than a second, one element greater than a second, a third element greater than a fourth, but then no greater than or less than relationships between the two pairs. We could have a chain of 3 elements and then an element on the side which is greater than the least one, and that thing upside down also. We could have 2 elements which are each greater than 2 other elements. We could have 2 elements greater than another, which is greater than a third one. And then some variations on that. We could have a chain of 3 elements and one on the side, and then a chain of 4 elements. Well, there should be 16. Let's see if I remembered all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's good. Now the fourth Catalan number is 14. So we have 2 posets here more than a Catalan number. So 1 over n plus 1, 2n choose n plus 2 when n equals 4. Now one way to think about a partially ordered set is to think of it as a directed graph. Usually we write poset for partially ordered set. So it's a directed graph, which is transitive and acyclic. Transitive means if we have an edge from x to y and an edge from y to z, then also we have an edge from x to z. Acyclic means either we have no edge from x to y, we have an edge from x to y but none from y to x, or we have an edge from y to x but none from x to y. So we can't have this cycle here. And the diagrams that I have drawn are called Hasa diagrams. So Hasa diagram represents x less than y as x down here and y up there. Equivalently, this is x with an arrow to y, a directed edge from x to y. So these diagrams that I drew for one element posets, two element, three, and four element posets are called Hasa diagrams. Another point of view is that a poset is a relation which is transitive, acyclic, and anti-reflexive. So transitive means if x is less than y and y is less than z, then x has to be less than z. Acyclic means at most one of x less than y and y is less than x, not both. Anti-reflexive means that x is not less than x. We write x is less than or equal to y for x less than y or x equals y. X equals y meaning they're the same element. That's the only way two things can be equal in a poset is if they're actually the same element. Now we call a set that is totally ordered. Let me say this. Call a totally ordered set a chain. Elements with no comparison between them incomparable and a collection of pairwise incomparable elements in anti-chain. So for example, if we put the poset of subsets up here again, zero, 2, 1, 2, 3 is a chain. And one, 2, 3 is a 2-element anti-chain. Of course, 1, 2, 3 is a 3-element anti-chain. Because none of these is less than any of the others, and here with 1 and 2, 3, even though 2, 3 is higher in the picture, 1 is not less than 2, 3. So those two are incomparable. Therefore, they form a 2-element anti-chain. The end.